In this lesson, we look at how computers represent text. We will see how letters, numbers, punctuation marks, symbols, and emojis are converted into numerical codes that can be stored as binary. A computer does not store the letter A directly. It stores a numerical code that has been assigned to the letter A. That number is then represented in binary. The same idea applies to every other character. A character may be a letter, a digit, a punctuation mark, a mathematical symbol, or an emoji. A character encoding is an agreed mapping between characters and numerical values. Once that mapping is defined and agreed on, the computer can store and process text using binary. Let's begin with a simple example. Suppose we create our own character encoding using 3 bits. 3 bits give us 2 to the power of 3, which is equal to 8 possible binary patterns. We could assign 000 to A, 001 to B, 010 to C, and continue assigning the remaining patterns to the other characters. The binary pattern does not naturally mean the letter. Its meaning comes from the encoding that we have chosen and agreed on. If two systems use the same encoding, they interpret the same binary pattern in the same way. If they use a different encoding, the same pattern may represent different characters. 3 bits are clearly not enough for all the characters we use. Even 4 bits only gives us 2 to the power of 4, which is equal to 16 possible patterns. That is not enough for the 26 letters of the English alphabet, even before including uppercase letters, digits, spaces, and punctuation. One of the earliest widely used character encodings was ASCII. ASCII stands for the American Standard Code for Information Interchange. It was developed mainly for English language communication and computing. ASCII uses 7 bits. 7 bits provide 2 to the power of 7, which is equal to 128 possible codes. These codes include letters, digits, punctuation marks, spaces, and control characters. For example, uppercase A has the decimal code 65. Its 7-bit binary representation is 1000001. When stored as an 8-bit byte, it is commonly written as 01000001. Lowercase a has the decimal code 97. Its 7-bit binary representation is 1100001. Stored in a byte, this becomes 01100001. Uppercase and lowercase letters may look similar to us, but they have different codes. The character 5 also has its own ASCII value. In ASCII, the character 5 has the decimal code 53. This does not mean that the numerical value 5 is stored as 53. It means that the written symbol 5 is assigned the character code 53. This distinction is very important. The numerical value 5 and the text character 5 are different kinds of data. The number may be stored using the numerical binary representation. The character is stored using a character encoding. ASCII also assigns codes to punctuation marks. The exclamation mark has the decimal code 33. The full stop has the decimal code 46. The question mark has the decimal code 63. Even the space has its own code, which is 32. A space may look like nothing on the screen, but it is still a character that must be stored. ASCII contains 128 codes in total. There are 33 control characters. These were originally used to control devices such as teleprinters and communication terminals. For example, some codes indicate the start or end of text. Others represent actions, such as moving to a new line. These control characters are not normally displayed as visible symbols. They instruct the system to perform an action. ASCII contains 95 printable characters, if the space is to be included. Since the space is not visibly printed, there are 94 visible printable characters. Now let's encode a complete word. Consider the word cat. In ASCII, uppercase C has the decimal value 67. Uppercase A has the decimal value 65. Uppercase T has the decimal value 84. So the word cat is represented by the sequence 67, 65, 84. Stored using 8-bit groups, these become C is equal to 01000011, A is equal to 01000001, and T is equal to 01010100. Putting these bytes together gives us the stored representation of the word cat. The computer reads the bits according to the ASCII encoding and reconstructs the characters. The same bits would have no fixed textual meaning if the computer did not know which encoding to use. ASCII works well for basic English text, but it is too limited for modern communication. It cannot represent many writing systems, mathematical symbols, currency signs, and other characters used around the world. Unicode was developed to address this problem. Unicode assigns characters unique numerical identifiers called code points. For example, Latin letters, Greek letters, Arabic characters, Chinese characters, mathematical symbols, and emojis all have their own Unicode code points. A Unicode code point is usually written using the letter U followed by a hexadecimal value. For example, uppercase A has the code point U plus 0041. The plus sign separates the label U, meaning Unicode, from the hexadecimal code point. So, U plus 0041 means Unicode code point 0041 in hexadecimal. The plus sign is only part of the notation. It does not mean literal addition. Unicode defines a code space extending from U plus 0000 to U plus 10FFFF. This gives us more than 1 million possible code points. Not every position is assigned to a character, but the space is large enough to support writing systems and symbols from around the world. Unicode defines the identity of each character. However, the code points still have to be converted into bytes before they can be stored in memory. This is done using a Unicode Transformation Format, or UTF. The most common formats are UTF-8, UTF-16, and UTF-32. UTF-8 uses between 1 and 4 bytes for each encoded code point. It is a variable in length. ASCII characters uses 1 byte for UTF-8. This means that UTF-8 preserves the original ASCII byte value. For example, uppercase A is stored as the same byte in both ASCII and UTF-8. Characters outside the ASCII range use additional bytes. Consider the word cafe. The characters uppercase C, lowercase a, and lowercase f each use 1 byte in UTF-8. The accented character E uses 2 bytes. So the word has 4 visible characters, but it requires 5 bytes in UTF-8. This shows that the number of characters and the number of bytes are not always the same. A character is part of the written text. A byte is a unit of storage. UTF-16 uses 1 or 2 16-bit code units. This normally means that a code point uses either 2 or 4 bytes. Many commonly used characters fit into 2 bytes. Other characters require a pair of code units and therefore use 4 bytes. UTF-32 uses 1 32-bit code unit for each code point. This normally requires 4 bytes. The advantage of UTF-32 is that each code point has a fixed length representation. This can make some kinds of processing simpler. However, it usually requires more memory. Let's compare the storage of a simple English word. Suppose we store the word book. In UTF-8, each letter uses 1 byte, so the word uses 4 bytes. In UTF-32, each code point uses 4 bytes, so the same word uses 16 bytes. UTF-8 is therefore much more space efficient for text made mainly from ASCII characters. However, the most efficient encoding for a complete document depends on the characters it contains. It is not always correct to say that one encoding is best for a particular language. Now consider a short message containing an emoji. Suppose we store hi! Exclamation. The H, I, and exclamation mark are all ASCII characters. In UTF-8, each one uses 1 byte. Now suppose we add a smiling emoji. The emoji may use 4 bytes in UTF-8. The displayed text contains 4 visible characters, but it uses 7 bytes. This again shows why characters and bytes should not be treated as the same thing. There is another complication. A visible symbol is not always represented by exactly 1 Unicode code point. For example, an accented letter may be stored as 1 combined code point. It may also be stored as a normal letter followed by a separate combining accent. The 2 forms may look identical on the screen even though their stored code points differ. This means that a visible symbol, a Unicode code point, and a stored byte sequence are related ideas, but they are not always identical. The intuition behind textual data representation is that computers store agreed numerical labels for characters. ASCII provides a small encoding that is mainly suited for basic English text. Unicode provides a much larger character system that supports writing systems and symbols from around the world. UTF-8, UTF-16, and UTF-32 describe how Unicode code points are converted into bytes. Text representation works because computers and software agree on how characters are mapped to numbers and how those numbers are stored as bytes. This shared standard is what allows the same text to be saved on one device, sent across the network, and displayed correctly on another.